Yeah, it's super helpful for field work.
Yeah,
Like,
definitely.
like,
Yeah.
what time does the rain come
Yeah.
tomorrow? Um, okay, so in respect to kind of physical parameters, or I guess the output of your model, like what parts are the most difficult to accurately predict or to accurately model or even to input, right? Like
Yeah.
what are the challenges in terms of parameters?
So, one of the biggest challenges, and it's also sort of a very important one, and it's important globally, right? Whether you're in the high latitude regions, so the North and South Pole, whether you're in the Amazon, or whether you're in the mountains of Idaho, is clouds, right? Clouds are notoriously difficult to model, and there's a variety of reasons for that. The in our neck of the woods, right, we're particularly interested in how the terrain interacts, right, how the topography interacts with the atmosphere, and how that leads to the production of clouds and ultimately to the production of precipitation. And I teach a sophomore level water in the West class. One thing we go through there, right, is that to have a cloud, let alone a raindrop or snowflake fall, right, there is a sequence of events that have to happen that are all really remarkable. And if any one of them doesn't happen, you don't get the precipitation. So precipitation in these models and clouds are really hard just because you have to get each and every one of that sequence of events right.
Is that I would imagine that's a pretty hotbed of like future research, right? Trying to smooth that problem out.
Yeah. So I mentioned Will. He's this is one thing that he's interested in, right? Like how do we represent the physics at the scale of individual sort of snowflakes, and how do we we can't model every individual snowflake. So how do we, in general, at the scale of like a kilometer, say, how much water here is in the liquid phase versus the solid phase? How much of it is solid phase and large enough to kind of fall out of the atmosphere? Very active area of research.
Sounds simple.
It's right. Yeah, exactly.
Like easy. So, one of the things that I think doesn't come as a surprise to a lot of people is when we look at climate models, most of them show a changing climate going forward. Depending on what parameters are built in, right? So, we or in an earlier video I talked about how like energy balance models, from 150 years ago, basically just predict stasis.
Yep.
Because they're not having these like changing variables going forward, and obviously we're much further along than that. But so if they show us change, can they show us like potentially what's causing that change?
Yeah, a lot of times so they can, right? And more than that, they help us reveal, kind of what we can think of as the chain of events that lead to the change that we see, right? So the models are sophisticated enough that we can actually, right, what we actually do, and this is where those scenarios come in, is that one of the forcings of the model is how much carbon dioxide, how much methane is being released from the land masses of the earth through energy production, through land use change, through transportation, right, through agriculture. And all of that carbon dioxide winds up from the modeled land surface in the atmosphere. And then it affects that radiation balance, right? It goes through the whole sophisticated energy balance calculations. And then it has all of these processes to redistribute the additional energy that's stored because of those additional greenhouse gases. And then that sets off a whole sort of sequence of cascades of changes to clouds, changes to precipitation, the way that the Earth system, the climate system, dissipates that extra energy. And it absolutely sort of helps us understand, right? When you do this, right? We can think of these climate models and the scenarios kind of big if statements, right? If this is what happens, then these are the things that happen, right? And so it helps us, as we generate those model simulations, also then interpret the observational data that we have to sort of say, okay, this model here suggests this, which is more consistent with what we see over here. So we think that actually like this process that this model is simulating is actually maybe what's actually happening.
Okay, so we can actually run models that basically model the Earth as if humans didn't exist, and we can compare those to models, which have all these variables in them.
Yep, absolutely, okay. Yeah, and in fact, I mentioned
not
this
that humans shouldn't exist.
Right, yeah.
That's not what I'm saying.
I mentioned those historical runs. One era in particular that is almost all of the climate models use it as an experiment, as a benchmark, is the Pleistocene-Eocene thermal maximum, right? Because we have really good observations. Not relative to contemporary, but we kind of know what was happening. And there weren't humans, right? So we can't invoke humans as causing global warming then. So it's a good way to understand like how the models, right, how well the models actually respond.
Cool.
So.
Yeah, there were like woolly rhinos and giant armadillos
exactly,
and.
Well, it's a side note, right? An interesting thing that has been making rounds on Twitter is that somebody has just taken a climate model and modeled the planet on Dune.
Oh, cool.
To ask, actually, could humans inhabit that?
You know what? I saw the headline and I scrolled right past it.
Yeah.
I will dig into that. Okay, so clouds, right? Clouds most difficult. That's actually something that we've touched on a few weeks ago. So we've been talking about computing power. Do you have a supercomputer? Like how? Like where does this work? Or like you're not obviously doing this on your laptop at home, right?
Right, yeah. So we use, there's a variety of these shared supercomputers across the country and across the world. They exist at a lot of places like national labs. So Idaho National Lab out in Idaho Falls has several large supercomputers. We use them and we do our simulations on those supercomputers. There's another big one in Cheyenne, Wyoming. That's associated with the National Center for Atmospheric Research, which itself is in Boulder. But yeah, this is the way that a lot of computational research is done, is that we use these supercomputers that are kind of shared amongst a variety of people. And quite frankly, a lot of them, it's not just climate modeling, right? So the INL one is doing a lot of what goes on inside nuclear reactors, and also some cybersecurity stuff. So
they're just strong enough to do modeling in general.
Exactly.
Right?
Yeah.
Like I've actually seen some stuff about COVID modeling.
Yes.
Right?
Yeah. That's been a big, huge topic in the past couple of years.
So then, are most of those funded essentially at the government level? Okay.
Yeah. So most of those are funded by so the one in Cheyenne is funded by the National Science Foundation. The one at Idaho National Lab is funded by Department of Energy, right? So the big federal government enterprises are, right, they recognize that, hey, there's a lot of modeling going out there on questions we need to know answers to, COVID, climate, cybersecurity. So it's worthwhile for us to invest in these computational resources so we can get those answers to those questions.
Okay. So if a student were to be interested in this stuff, or actually, so how did you get interested in this stuff? Like, what was your path to climate modeling?
Yeah, so I was actually my undergraduate is in civil and environmental engineering. I didn't really know, right, when I was in that, it was sort of well, this is a good, right, like there's always going to be a career in civil and environmental engineering, right? We always, need people for roads and bridges. And I just got fascinated in water. I grew up in Colorado. And so I started, and really kind of about the time when there was a lot of, news articles and a lot of papers coming out about like, hey, climate change, the Western U.S., this is going to be a big thing. And so I got into this, as an undergraduate, and the computer side specifically came in that I've kind of always enjoyed, going back to my childhood,
right.
I built a lot of plastic models, right, and like model airplanes and stuff.
Yeah,
and so I always loved like tinkering right? Whether that was with a plastic model, or whether that was like with the computer. And so I just gradually got into more kind of quantitative parts of the earth and environmental sciences, and gradually just sort of like got into it that way, right? And so our group does a lot with tinkering with models, right? Playing with them, maybe tweaking some things here and there, and yeah, asking it to tell us what happens if we poke
Right,
the model
yeah.
in this way.
So then if a student were to be interested in pursuing this, or at least, kind of further investigating, is it like a computer science track? Is it a geology track? Is it a kind of meteorology track?
It could be any of those, right?
Okay.
And I think that that's one thing that I underscore to students all the time is that we have needs for all of those specialties, right? If folks are interested in computer science, these models are big and complex. Computers are big and complex. We're always looking to do things better, to do things faster, so that we can run more interesting questions, right? More interesting experiments. We obviously need, the people that, study and understand the individual, processes that go on in the Earth system. Whether that's, geoscientists that are understanding kind of, more of the physics of these kinds of things, whether that's ecologists that are understanding, kind of the role of ecosystems and in connecting it, and engineers as well, right? That that can kind of help with both some of the quantitative facets, but also increasingly, some of the some sophisticated things, right? Like geoengineering is becoming a big question mark. So
What's your favorite type of geoengineering?
I would
Or like most intriguing? I
Most
guess.
intriguing.
Yeah.
I think I don't know that I have like solar engineering is scary, right? Just because like populating the atmosphere with a bunch of particles is
Oh, it's like
sort of
that's the
scary.
sulfur dioxide.
Yeah, the sulfur
Yeah.
dioxide thing.
I like it though.
Yeah, right. Yeah,
Pretty scary.
Yeah, it is. Yeah, so I think the bottom line is that a lot of these, right, there's a lot of pathways to this, and all of them are really important.
Right. Yeah, carbon. What was it? Elon Musk is paying for carbon stripping. That's the news of the week.
Yeah, exactly. Like carbon air capture is like a big one that is I'm skeptical that will work. The one that I think could work is actually is the more kind of precipitation of calcium carbonate in the soil. Like I think that actually could,
Yeah. Yeah, like long-term soil carbon
Yeah.
storage.
Yeah, exactly. Yeah.
Cool. Do you have a favorite local weatherman?
Do I have a favorite local weatherman?
I guess we're kind of past the days of local weatherman.
Yeah, I have interacted a little bit with Bree Eggers at
Okay.
KTVB, and she's wonderful, a great person. Have chatted with her a few times. She's definitely a favorite. We work actually the folks at the weather forecasting office, so Jay Breidenbaugh, up there at the airport. We get to geek out on weather a
Right.
lot because
Right.
they're the forecasters and we're sort of the scientists, so there's
Right.
like a nice exchange there. So
All right.
yeah.
Well, this has been great. Thanks
Yeah.
so much for
Thanks,
taking
Andrew.
a little bit of time out of your afternoon, and hopefully the students enjoy it.
Yeah.
All right.
Reach out whenever. I love talking to students and geeking out about
Yeah,
this.
I'll actually include the contact information in case anyone wants to shoot an email or anything like that.
Awesome.
All right. Well,
All
thanks
right.
again.
Yeah, thanks, Andrew.
All right.
Okay.
Oh, well, that was good.
Yeah.